the harder problems, but we can get the idea here, okay? Okay, so first of all, we've talked about what functions are. What we haven't talked about is what a one-to-one function is, okay? And this kind of thing shows up a lot of times when I teach trig. I was teaching trig the other day. I had to remind students about what one-to-one functions were because of what the graphs that we did in trigonometry. So what this says is, this is the definition I think our book uses. It says, if any two different inputs in the domain correspond to two different outputs of the range, a given element in the range must correspond to one and only one element of the domain. That to me is kind of wordy, okay? It's just as easy if I explain it this way, okay? And I think the way you ought to write this is like this. I would write this down instead, okay? If every y value, or let's just say every y, okay? If every y has exactly one x, okay, then it's a one-to-one function. Okay, it's totally in reverse of what a function is. Okay, when you learn about a function, you learn if every x has one y, then it's a function. Now it's backwards. If every given y has one x, then it's a special function called one-to-one. Okay, so the best example of this is Cindy, Jan, Marcia, Bobby, Peter, and Greg. Are you guys don't know what I'm talking about, or are you way too young? Okay, Brady Bunch. Most of you are probably too young. Gosh, okay, that's back in my day. Okay, so here's the idea. Bobby, one girl. Peter, one girl. These are brothers and sisters, by the way. Okay, Greg, Marcia, like this. Okay, that's a one-to-one function. That's why it's always going to look is the y is matching up with one x right here. This is your x, that's your y. So does every y have exactly one x? Yes. So it's a one-to-one function. It's totally backwards of what a function is, okay? All right? So let's take a look at this. You start here. Marilyn, how many x's? 1. Lucy, how many x's? 1. Peggy, Curly. Okay, that is yes. So that is a one-to-one function. That's what it looks like, okay? Every y has exactly one x. Okay, look at the next one. Look at Al. How many x's does Al have? Okay, he has 3. Okay, so that is not a one-to-one function. Okay, it is a function, but it's not a one-to-one function. Remember, a function is does every x have one y? So is this a function? Yeah, this, Cindy, L, Jan, L, Marcia, L. That's a function. It's just not one-to-one. Okay? All right, let's take a look at this next situation here. Okay, so let's see. The question is, does every y have exactly one x? Does Alice have one x? Yeah. Linda? Yes. Carol? Yes. So the answer to that question is yes. But you got to be careful about this. Okay, I'm asking, is this a one-to-one function? Okay, is this a function? Okay, how do you tell if something's a function? Does every x have exactly one y? Does it work this way? Does Sam have one lady? Okay. No, he's got 3. He's a bad boy, right? So that's not a function. So it's not one-to-one either. Okay, it's got to be a function in order for it to be one-to-one. Okay. So the thing on this is, you might write a note on this, is it's not a function. So you got to kind of remember what a function is. All right. So it's got to be a function and one-to-one. All right, that's the way that works, okay? All right, let's look at this next one. Now, this situation right here, one thing that's kind of helpful, if you need to do this, is just to write down all the x's. So we have the 0.26. You can write what's called a mapping diagram. So you can say 2 maps to 6, and you can say 3 maps to 4, and you can say 5 maps to 8, okay? Does every y have exactly one x in this problem? Yes. Is this a function? Yeah, every x has a y. So you got to do it both ways. Okay, so that's a one-to-one function. Okay, you have one x, you have one y. It goes both ways. Okay, that's one-to-one. That's why we call it one-to-one. Okay, next one, let's just kind of make a similar diagram. So this is -3 maps to 4. Then we have -2 goes to the same thing. Okay, then we have -1 goes to 2. And then we have 0 goes to 6 like that, okay? So answer the question. Does every y have exactly one x? No, we have a problem, okay? That 4 has 2 different x values, so what's the answer? It's not one-to-one, okay? So that's not a one-to-one function. It is a function, it's just not a one-to-one function, okay? That's the idea, okay? All right, does that make sense to you guys? Okay, it's just to think of everything in reverse. Every x has one y as a function. Every y has one x as a one-to-one function. It's got to satisfy both conditions. Okay, one of the things we already learned that the way you can tell if a graph is a function is by applying the vertical line test. Okay, so if you look at this example 1, the vertical line test tells you if it's a function or not. Is this a function?
Yes.
Yes, because it only goes through one point. What you're doing on this is you're proving by doing that every x has one y. That's what you're doing. A lot of times students don't understand that, but they understand how to do the vertical line test. Okay, so that one is definitely a function. Okay, now I'm going to erase that. Now we do what we call the horizontal line test, and this is how you test if something's a one-to-one function. Okay, if I draw this horizontal line, how many points does it go through? It goes through 2. So it's not a one-to-one function. Now what that's doing, and you want to understand this, is this just showed if you have the same y. Those 2 points have the same y. They have 2 x's. That's why it's not one-to-one. It's because you have the same y, 2 x's. That's what the horizontal line test does. Okay, it applies that definition. Okay? All right, let's look at example 2. Vertical line test. Is that a function? Yes, it's a function. Okay? How about the horizontal line test? Does that work or not work? That works. Okay, so that is a one-to-one function. That's the way one-to-one functions look. Okay, like that. Okay, let's see. The next example, I think this one is a just a horizontal line. Okay, does that pass the vertical line test?
Yes.
Vertical line, this way. If you do vertical lines, that only goes through one thing, right? So that's a function, right? Okay. All right, now how about if I do the horizontal line test? Does that pass? What would happen if you did a horizontal line through a line that's already horizontal? It would pass through in every single point, right? So it's not one-to-one. It can't be. Okay? That is a function. It's just not one-to-one. Okay? All right, how about example 4? Is this a function? No. So automatically it's not one-to-one. It would fail the horizontal line test anyway, but it's not a function, therefore it can't be a one-to-one function. Okay? That's the idea. Okay? Everybody solid with that? Okay? Usually that's not a big problem for students. Now this theorem right here, I want to just talk about what this is talking about here. So I want you to just draw a little XY axis on this, on both of these. And what we'll do is what this problem says, a function is increasing on an interval, I, is one-to-one on I. Okay, so here's what I'm talking about. Let's put like an AB. We're just have an interval from A to B. If we made a function that was increasing, it would have to look something kind of like this. The y values would have to get bigger. Now, is that a one-to-one function? Yeah, how come? Passes the horizontal line test. Good. So that's what happens if it's increasing, that has to happen. So it's one-to-one because of that. Okay? Let's do one that's decreasing. Okay? Same idea. Here's A, here's B. Let's draw a function that's decreasing. There's all kinds of ways you can draw it. You could draw it with a straight line. Okay? Is that a one-to-one function? Yes. How come? It passes the horizontal line test. Okay, exactly. So that should be logical to you. If a function's increasing, it's one-to-one. If it's decreasing, it's also one-to-one. Okay, it can't change though. Once it changes from increasing to decreasing, it can't be one-to-one anymore. Okay? Okay, so I think we'll have time to just introduce the idea of an inverse. Not get too heavy into it, but the basic idea. Okay, so an inverse of a one-to-one function, and basically you only have an inverse if it's a one-to-one function. You can't do an inverse if it's not one-to-one. Okay? We notate this like this, f inverse of x. Okay? Maybe you've seen that before. That's not an exponent. That means it's an inverse. If you take trig maybe in the next semester or pre-calc in the next semester, you'll see inverses a lot. So all it is you interchange the variables, okay? So this particular problem right here, the first thing you got to do is you got to make the decision on whether it's one-to-one or not. If it's not one-to-one, it can't have an inverse. So let's just figure this out. So we have the point 110, we have the point 220, then we have the point 330. Okay? Is that a one-to-one function? Yeah, how come?
Because each y has an x.
Oh, you said it perfectly, just like a mathematician. Every y has one x, so therefore you're good. Okay? Excellent. So here's what you do. Your inverse goes like this. You just switch the points backwards. Instead of 110, you say 10, 1, then you say 22, then you say 33 like that. That's it. That's all you do with inverses. It just means the points are backwards. That's the idea. Okay? But you can only do that if it's one-to-one, because if it's not a one-to-one function, then your inverse will not be a function. Okay, so that's the idea. Okay, let's run through this, this kind of situation right here, and I'll talk about what this is. I'll just demonstrate this in a couple of examples then. So if you have a one-to-one function, then what happens is if you do the composition with its inverse both ways, you end up getting x. Okay, that's what I'm going to show you. Then we'll talk a little bit about there's a certain symmetry to this also. Okay, so I'm going to demonstrate that to you in this problem. Okay, first of all, I've given you two functions. So we're going to start with doing a graph of 3 minus 2x. Now we're going to do some points because this will help you understand something, hopefully. Okay, so on this little table of values, this is a line. So all I care about is just 2 points. So let's just let x be 0. And then let's also pick maybe one other point, like just a 1, like that. Just keep it real simple. So if we work this out, if we have f of 0, that's going to be 3 minus 2 times 0. So I'm working with this function that I highlighted in yellow. So 3 minus 0 is 3. So let's put that point on the graph. That's a point 0, 3, and label that because I want you to kind of have a good picture of how inverses look. Okay, now let's do f of 1, doing the same thing. So we're going to do 3 minus 2 times 1. So that's going to be also 1, so you get a point 1, 1. Okay, so let's plot the point 1, 1 and label that like that. Okay, let's do one other point too. I want to go ahead and do one more. Let's do 2. So if we do f of 2, we'll have 3 minus 2 times 2. So that is 3 minus 4, which is negative 1. So we're going to have a point 2 and negative 1 like that. Okay, and then just connect the dots. That's a straight line. We already know that's a straight line. Okay, all right. Now, what I'm going to show you on this is, I'm going to try to be kind of careful when I do this now, is we're going to now work with this function. Okay, so this function is g of x is equal to negative 1/2 times x minus 3 like that. Okay, so let's see. I'm going to give you certain points. I know there's a reason why I'm doing this too. Let's do 3. Okay, let's do 3. So let's do g of 3 and see what happens. Okay, so let's plug in 3 into this function, see what happens. That's negative 1/2 times 3 minus 3. So what is that?
0.
0. Okay, so we got that. What do you notice? 0, 3, what happened? It's now backwards. Okay, that's kind of what we're looking for. Okay, so let's go ahead and let's plot that then. So we got go over 3 and then do that like that. You don't have to label that. I was kind of getting kind of cramped up there. So we have that. Okay, next thing I want you to do is I want you to do g of 1. Okay, let's let x be 1. So if we do that, we would have negative 1/2 times 1 minus 3. You would plug that in. That would give negative 1/2 times negative 2. That's negative 2 over 2. Therefore, not negative 2, positive 2 over 2, so that's 1. Look at that. We have the point backwards. If you flip 1, 1, it's still 1, 1. Okay, so that's working out. Okay, then let's do one more thing. Let's let x be negative 1. So we have g of negative 1, and let's see what happens. Okay, so if we do that, we'll have negative 1/2 times negative 1 minus 3. So that's negative 1/2 times negative 4. So that's 4 over 2. So that's 2. Okay, so here's what I'm wanting you kind of see on here. All right, these things are flipped, right? 0, 3, 3, 0. 2, negative 1, negative 1, 2. These things are going to be inverses of each other. So let's go ahead and let's finish plotting these 3 points. We have 3, 0, we have 1, 1, and then we also have negative 1, 2. So if you move over like that, then you want to go like this. Okay, so that would be, and I want you to label this like this. You need to have this labeled. This is f of x. The one in red is f of x. The one in green is f inverse of x. Okay, like that. Now we're going to do one other graph on here to kind of show you what happens. So we're going to also graph y equals x. Okay, so when we do that, all we need is 2 dots. Okay, let's just say negative 2 and 2. Okay, when you do this, if y is equal to x, that just means x and y are equal. So if you plot those 2 points, if you plot negative 2, 2, negative 2, negative 2, you'd be there. Then if you plug 2, 2, you would be there. And then I want you to just kind of draw a dashed line. It really goes at a 45-degree angle, and that's y equals x. Okay? So what happens on inverses, if you can imagine taking a piece of paper and folding over that diagonal line, wouldn't these things come together? Okay, just think what I'm saying is fold like this, they would come together. That would match that, that would match that. Okay, and that's the way one-to-one functions are, is they're symmetrical about y equals x. They always will be, so you can use that kind of a way to visualize this. Okay, let's go ahead and finish up with doing this next here. So we're going to go ahead and do f composed of g of x. Okay, so we've learned how to do compositions. Let's just do this both ways, and then that'll be a good stopping point for us. Okay, so if we do f composed of g of x, we do 3 minus 2 times something. What goes into the bracket? The other function, g of x, exactly. So you plug it in. Okay, now you're going to simplify it, and if it turns out to be x, that means it's an inverse. So what will happen here is you can do this. This would be 3 plus. Now if you multiply that out, that's going to be 2 over 2 times x minus 3. And it's a negative times a negative. That's why it's plus 2 over 2. So that's going to be 3 plus, that cancels out, x minus 3. 3's cross out. That's going to be x then like that. Okay? I'm going to erase this, and we're going to do this backwards. Okay? Now let's do it backwards. Let's do g composed of f of x and see if we get the same thing. If it is, that will prove that these are inverses of each other. Okay, so what we have is if you do g, you want to write down negative 1/2 times something minus 3. Okay, so just start by writing down g, and then what goes into the parenthesis? The other function. So you put in 3 minus 2x like that. Okay, work it out algebraically. We'll see what happens on this one then. So what you'll do on this is notice the 3's cancel out. So that would end up giving you negative 1/2 times negative 2x. Okay, so that will give you 2x over 2. So what's that equal to? X. So here's what you kind of find on this. So if you do your composition both ways, then we would say, therefore, we would say f and g are inverses of each other. Okay, that's the basic idea behind that. Is what I wanted you to see is the points are backwards. They're symmetrical about y equals x, and if you do the composition, you get x. Okay, you get that line of symmetry. That's how that works out. Okay? All right, does that make any sense for starters? Okay, we'll work on this a little bit more next time and finish this up. All right.